Hello again, YouTube. This time back to fundamentals. In a previous video I did this project, which was a simple bit bang of serial transmission. So RS-232 would have been the original standard back in the 60s. I'll link the previous video. I mean, it's very basically you're just pushing out bits, the bits that make up H, which is 48 hex, onto the serial line. So we're just using D0, and it's basically like Morse flashing a light, except the timings are much more accurate and faster, because these timings, the delay I have here was calculated for 9600 roughly. So I've added an extra delay here at the end to what we had, so we can easily trigger it on the Sealy logic probe. So the Sealy logic has, this is the output, so we can see our H getting transmitted at a regular interval. So that's bit bang, and you would never consider doing that, but it just shows you that the makeup, like the Morse code, you're just turning something on and off. It's just there are 8 bits now as opposed to dots and dashes. So if I quit out of that project, the other project that is actually, if I open it from this, it's down in the libesoup in the examples directory. There's projects and microchip, which is the only thing we're using at the minute, and this UART transmit, UARTX, and all that file does is, I mean, if we just look at the lib config file, it basically, I'm including hardware timers again because I'm using a delay, and I turn on the switch, the compiler preprocessor switch for the system's UART. So I want UART code, and the transmit buffer size on 200 bytes is more than enough for what I'm going to do here. That will depend on how quickly you're emptying and filling up a buffer. So it's to do with your producer of data and your consumer of data. In this case, the UART, the Silicon's UART peripheral is the consumer of this. It'll empty that buffer of 200 bytes. So everything revolves around this UART.h down in libesoup comms UART.h, and it defines the various pieces of configuration that you need. So data bits, number of data bits, parity, stop bits, idle high or low. Usually it's idle high, and there is little Indian and big Indian, but default is to little Indian. So I think the default is little Indian anyway, least significant bit first. So everything we communicate with the UART functions, API functions, is through this structure, this UART data structure. So we pass a pointer into the functions, and we specify a transmit pin and a receive pin, or we specify one or other. So if we only want to transmit, in this case we only want to transmit, so we're only going to fill in a valid pin for the transmit pin. Now the index we don't mess with because that's filled out by the libesoup code. We specify a mode, which is a bit field that's going to be programmed into the special function register of our microcontroller, in this case the DSPIC33. So we will pass, there's a function we'll see in a minute that you pass in the configuration you want specified with these constants, and it will fill out the mode. And after that, all you do is specify a baud rate, and you can leave transmit finished, that callback function, null. But basically, if you want to be notified when the transmitter is finished transmitting and the buffer is empty, then you can set that function to a callback. And in the same way, if you're receiving characters, you need a function which is going to receive the characters. I'll do another example on receive, but at the minute that's transmit, and there's only a few API functions that you call. So we're defining that UART structure. Now we have to fill it in, so we're going to call this API function, which is calculate mode. So we pass in the UART mode, the address of that U16, which is the value that we're then going to end up programming into the special function register, and we set the number of data bits, the parity, the stop bits, and idle high. And then once we've done that, fill out the transmit pin. So we're going to transmit an RD3. The receive pin is invalid, so we're not going to receive anything. And then we'll set the baud rate 9600. So that's the same baud rate as we used the last time. And we'll set the transmitter to finished. And then we just call a reserve. Now if multiple people are using UARTs, or multiple elements of our application are using UART, it will just grab the first free UART and reserve that. So we're reserving this for our use and nobody else can now use it. And we pass in the address of that structure, so the API code sets up now the pins and the configuration that we've selected here and the baud rate. So it sets everything up, and then I'm delaying for a few seconds to give me Sentinel a chance to just trigger on the Sealy logic, the pulse view, and then we transmit the buffer, which we've defined up as above as just hello world. So we're transmitting hello world, 13 characters. So that's all we're doing there. Transmit that string. And in all these cases, we are just checking for the return code. I use the convention where return code is negative, it's an error, and we'll just drop out. We'll light LED 0 and drop out, and that's it. So we only transmit this once. In the last example there, when we bit banged, I just kept transmitting the H character. So now we're just going to transmit this once, and this is our callback. So when the transmitter is finished, the transmit buffer is empty. We're going to light the LED on D1 and then just release that UART. We're finished using it, we don't need it anymore. So if I compile this and drop it in, flash it into the device, we should get a different outcome here. So if I cycle the power and start running, hopefully there's our hello world. So it's much simpler than our bit banging of H, and it's much simpler than playing with special function registers. We just do we just pass that setup, reserve a UART with a configuration and the transmit pins or whatever, and then we just call the transmit buffer. Now, the alternative to using Sealy logic is if we just take this and instead of going into a logic analyzer, if we take it into the Raspberry Pi, well, the FTDI Raspberry Pi serial connector cable. So we'll just connect ground, and the yellow is the RX. That LED on D1 was to indicate that our transmit had finished and we'd release the UART again. So if we do this with a Raspberry Pi serial connector, we can go to our terminal and Kermit. I'll just power off my device. And I'm going to set the speed 9600, carrier watch off, and connect. And now if I turn on, I made that 10-second delay a bit long. And that's it, hello world. The \n, I'm sure if you're used to C, \n, \r, new line is just new line carriage return. Sorry, I'm in the wrong. No, I'm on the right one. So yeah, the end of hello world, the \n/or, and that's all it is. That's it. It's as simple as that. So yeah, that example function is there. I'll try and do another example of receiving, and show you that next time. Again, thanks a million for watching.